All right, welcome to what is finally our last part of chapter 17 as we start getting into solubility equilibrium. So we're still going to be talking about an equilibrium kind of situation, but we're going to kind of relate this back to some things that we saw in 1211 in terms of solubility. And so all of these reactions are going to involve basically a solid being put in water and just breaking up into its individual ions. That's kind of the general reaction for these. And the equilibrium constant for that reaction is going to be referred to as KSP, or the solubility product constant. And it hopefully should kind of make sense. They call it this solubility product constant because if we're starting with a solid and going to its product ions in solution, the only thing that's going to show up in the KSP equation is just the products. Since the reactant will always just be a single ionic solid, the reactant's basically always going to be 1, or the denominator, the denominator in your fraction of your equilibrium constant is always going to be 1. And so that's kind of where that term or name comes from. So it's kind of a quick example for the dissociation of CaF2 as a solid into calcium 2 plus and 2 fluoride ions. Your KSP would simply be the concentration of calcium 2 plus times the fluoride ion concentration squared. Right now, again, this is something that we haven't had to deal with too much in a lot of the acid-base stuff. Coefficients are going to matter again. So like the fact there's 2 fluoride ions here that are being given off, though we do pay attention that here it's going to be a squared for its concentration in that KSP equation. Oops. Now, there's kind of when we're doing calculations for KSP, there's two kind of components as far as what we're trying to solve for all the time. We're either going to be looking for KSP or we're going to be looking for something else called the molar solubility. And those two things, they are different. They're not the same, and I really do want to emphasize that. KSP itself is an equilibrium constant. It doesn't have units, whereas molar solubility is the amount basically of your solid that will dissolve in 1 liter of solution. That's kind of the way I always think about it. And so it is listed in terms of units as units of moles per liter. It's the moles of your solid that will dissolve in the 1 liter of water. And it's effectively in units of molarity is what you're getting out of that. So it's called the molar solubility. Now, these two things, molar solubility and KSP, are related to one another. And one of the things that we're going to take a look at here with some different examples is if we're given one, we should always be able to find the other, and back and forth. So how does that work? Well, let me apologize for some weird spacing here on this all of a sudden. There we go. But let's take a look at an example. So we're going to look at finding the molar solubility of magnesium fluoride, MgF2, if its KSP is 5.16 times 10 to the minus 11th. And just as a general note, KSP values are usually really small. And when I say really small, like they can be like 10 to the minus 30 or 40 or something even. We'll see an example here towards the end as we get to the example problems of this section. Something that's like 10 to the minus 39, I think, in one of our examples. So it can be a very, very tiny constant. It's very, very rare that it's big, because usually if KSP is big, that's when we just have a compound that we typically consider as just soluble, right? Because if you think back to 1211, we always kind of talked about things as being either like soluble or insoluble, and we didn't have kind of this middle ground. And now we see that everything really is more of a middle ground in reality, and we can measure it. But when we start getting KSP values that are very big, that favor products rather than the reactants, that's when we get our compounds that we consider soluble in terms of kind of those designations. Now, for this particular example, if we want to solve this, so we have a KSP value, 5.16 times 10 to the minus 11, and for magnesium fluoride, its KSP in terms of writing an equation for it, right? This would be our starting solid. It's going to break apart into like 1 magnesium 2 plus and 2 F minus ions, which would be then the concentration of magnesium 2 plus times that fluoride concentration squared in terms of our KSP equation. Now, what I normally like to do, and this is where things maybe get a little bit different here, is that we're really making an ice table in a sense as far as like what we're actually doing. Is we're making an ice table for this basically this dissociation. So what I'm going to do, I'm going to swap to a whiteboard for a second. We're going to take a look at exactly how I set this up and where these X's come from. But these X's are really going to be our molar solubility. In some references, you might see them as a capital S instead. I like to use X's. It's just, I think, more consistent that way, and we're used to using X for our normal ice table setups anyway. Notice these are ice tables because tiny equilibrium constants not going to completion. So I'm going to take a break here. We're going to get to the whiteboard side of this so we can see how to set this up. All right, so swapping over to kind of my whiteboard view of things. the way I'm going to set this up is the first thing I'm going to do is just write that dissociation reaction, which is our magnesium fluoride as our, oops, just wrote that as a gas for I don't know what reason, as a solid, which is going to be associated into magnesium 2 plus, aqueous plus 2F minus, also aqueous. Now we're just breaking that ionic compound into its individual ions. And this is an equilibrium, so an ice table. And I have an initial concentration of my magnesium fluoride, or actually, I'm sorry, I don't have an initial concentration of magnesium fluoride because it's just a solid. Right? And so if it's a solid in terms of this table, there really is no left side of my reaction, which is interesting because the product side is zeros starting out, unless we're given some initial concentration of one of our ions, which we'll get to kind of in a moment. But then my change, I'd have plus x and plus 2x because of the stoichiometry. Right? If I have 2F minus, I'm going to be getting plus 2x as I set this up, which will give me x and 2x as my equilibrium amounts, which means I can write an equation where KSP should be equal to x times 2x squared. Right? The quantity 2x is squared because I have the two fluorides again. The 2x is, in this case, the change, and then it's getting squared because there's the two of them for the equilibrium constant equation. And then the x in this case is my actual molar solubility. Right? X is, in terms of what molar solubility is, it's the moles of my starting compound that dissolved in 1 liter of water. But for every 1 of magnesium fluoride that dissolves, I do get 1 magnesium 2 plus ion. So this concentration here, this X, that is the amount of this that's dissolved. And so X effectively is my molar solubility in this case. And if you set things up with the normal changes, like paying attention to stoichiometry, X in any table like this, when you set it up, just is your molar solubility if you're starting from the KSP. And now for solving the rest of this problem, it's just a matter of putting our KSP value in. So they tell us that our KSP is 5.16 times 10 to the minus 11. So I can say 5.16 times 10 to the minus 11 is going to be equal to, if I expand all of this out, 2x, the whole thing being squared is really 4x squared times x. It's going to be 4x cubed. And now I can solve this for x. I can take 5.16 to the minus 11, divide it by 4, and then I can take, to get rid of this x cubed, I take all of this left side to the 1/3 power. And I think I have this in the slides, so I'm just going to grab from here. Looks like about 2.35 to the minus 4 is what that comes out to at the end. And then unit-wise, since it's molar solubility, we are going to get molarity as our final unit. Right? If we're going the other direction, if we had the molar solubility, that's really kind of the only other real type of problem you probably see, at least early on in the solubility portion, is if instead of looking for the molar solubility, we're looking for the KSP itself, we can set up our equation for KSP and these x terms, right, for our changes, where x is the molar solubility, and if they give us the molar solubility, we're just plugging that in for the x's, and then finding the KSP. And that would be the only kind of difference as far as problem setup if we ran into that situation as far as what we're trying to solve. All right, now I'm going to kind of talk a little bit more about some general things with solubility, and then we'll look at a couple more example calculation problems. So let me pop this back up. And the other things in terms of like solubility that we want to kind of take a quick look at is things that actually affect solubility. And so we didn't talk about this really at all in 1211, so this is fairly new. And there's 3 main factors we're going to take a look at in this chapter. Excuse me. And those 3 main factors are going to be what we call the common ion effect, and then pH that we've been talking about now for a while, and then something called the formation of complex ions. And they're each a little bit different in terms of their impact. The common ion effect, we've seen this a little bit kind of in terms of talking like with buffers, how if we had something that was like kind of already in the solution, like as far as like our dissociation that was happening. So as like an example of what the common ion effect really is, like if I look back at my table here, like for the last example, like if I had this reaction, the common ion effect is if one of these starting concentrations would not be 0, right, in terms of like what that would do. And if I have one of these starting concentrations as not 0, the effect that's going to have is really like a Le Chatelier's effect, right, Le Chatelier's principle. If I add a product to this reaction, it's going to shift the reaction backwards, which means my x values that I end up solving for are going to be smaller if one of these starting values is not 0. And so that's kind of the main thing with the common ion effect. And that's the one of these 3 that we can actually do calculations on to really see what the solubility is after that common ion effect in terms of like what it's going to do to the molar solubility itself. Now, pH can also affect solubility. We could do the calculations on this, but we're not actually going to for this class. That's something that, again, like if it's really important, probably can see stuff like that again, maybe in analytical chemistry when we go a little bit more in depth on some of those things. But for here, the basic trend that I'd like people to be able to recognize is just that if your salt has a basic anion, that's the biggest thing we look for. If you have a basic anion for your salt, that means the solubility will increase as the pH decreases. And kind of the reasoning for that is your pH goes down, there's more H3O plus in your solution. If you have a basic anion and there's more H3O plus in the solution, those things can neutralize each other. And as a result, if you're removing the anion, right, your basic anion that you're forming when your salt dissociates, that's effectively removing a product, and so you are going to increase the solubility by doing that. Again, it's kind of like a Le Chatelier's effect at that point. But there is kind of the stipulation, your anion has to be basic for this pH to really have an effect. And then the actual trend is your solubility will go up as pH goes down if your anion is basic. Now, the last one, formation of complex ions, also is going to be more of a qualitative kind of thing that we're going to look at, and that's the fact that a lot of ions, if you have metal ions, like transition metal ions in particular, they can combine with just kind of common Lewis bases that might be in solution to make what's called a complex ion, which is basically just a metal cation surrounded by a bunch of Lewis bases, but the whole thing is still charged, so the whole thing is still an ion. And those formations are actually really favorable, and it's actually a way that we can help increase the solubility of a lot of our normal metal salts. And I'm going to talk about that more in depth kind of as I go through each of these three kind of more individually. So starting with the common ion effect, in terms of trying to kind of show a calculation example, here we're asked to calculate the molar solubility of magnesium fluoride in a solution that is 0.20 molar sodium fluoride, which basically this is exactly what we just did, right? So we've already gone through and found molar solubility of magnesium fluoride previously, right? We set all of this up. Now what's different is we're going to have an initial concentration of something. So they're telling us that our solution is 0.20 molar in sodium fluoride. Well, if that's the case, that just means now I have an initial concentration for my ice table. And so I'm just going to go ahead and kind of move this down, just set up a new ice table for this. So magnesium fluoride, going to magnesium 2 plus and 2F minus. I still have no magnesium 2 plus to start, but now I have 0.20 molar sodium fluoride to start. And that's just because they're telling me in the problem I have 0.20 molar sodium fluoride, which if you have sodium as part of a salt, it's pretty much going to 100% dissociate all the time. And so the sodium is just kind of almost ignore it. And so it's really 0.20 molar in fluoride ions in terms of this problem. And now the change is still the same that we would have before. We'd have plus x and plus 2x, minus x and 0.20 plus 2x. And now I can write an equation for my KSP. KSP would be x times the quantity 0.20 plus 2x squared. Except my KSP, if we just found this in the previous example, we found that our KSP for this, or sorry, we were given the KSP in the previous example for this one, was that, if I scroll back up, 5.16 times 10 to the minus 11. And so this means now that I can solve for this x. And I can still use, right, if I'm looking at my equilibrium constants really, really tiny, it's not going forward very far, which means x is going to be very small. So the x is small approximation does still work here. So we're going to use the x is small approximation. Which makes our math a little bit easier again. Sorry about that. And so using the x is small, now my KSP, which is this 5.16 times 10 to the minus 11, is going to be equal to x times 0.20 squared, which makes the math a lot easier, right, if I get to ignore that plus 2x part for my x is small approximation. And now when I solve for my x value, we're going to see here, I'm going to just kind of cheat and get it from the slide, 1.29 times 10 to the minus 9. So what I've done in these first kind of two examples that we've looked at, I've basically found the molar solubility for the same compound, just one in plain normal water and one that had some fluoride ions already there. And we see that if the fluoride ions were there, our solubility was 10, times 10 to the minus 9. But initially, without any of the fluoride there, it was 10 to the minus 4. That's 5 orders of magnitude different, right? So we're talking like about 100,000-fold, difference in terms of the solubility just by having that fluoride there. So it's a huge difference in those solubilities, and that's kind of really what you see out of this common ion effect is that if you have one of your ions that you're going to get from your salt dissociation already in solution, your solubility is going to go way, way down because of that. And it's really just Le Chatelier's principal effect at the end of that. All right. The last couple things, these will be more, like I said, kind of conceptual for this part. So here we have the effect of pH. And this is, probably should say chapter 16 here, so I'm just going to go ahead and fix this before I even blow up this slide. And so in kind of our previous chapters, we talked about how to look at if ions are if ions are basic or acidic. And so in this case, we have our anion in particular is what we're really focusing on. And that's really what we're trying to figure out, right? If the conjugate of the anion is a weak acid, the anion itself is a weak base. That was kind of how we looked at things. And so if the conjugate of our anion was a strong acid, then we consider that anion to be pH neutral. Those are kind of our two possibilities. And so for us, we're just looking at ionic salts and just trying to figure out, is the anion basic? And if the anion is basic, then it's going to follow this general trend. Where our solubility will increase as the solution gets more acidic, which means the pH is decreasing in those cases. And again, that's just kind of the Le Chatelier's effect. So we could try to do calculations for this by figuring out like what the pH is and relating that to things like OH concentrations, and eventually trying to set up our equilibrium and use that. It's not something we're going to be doing for this class. It's not important really for this class. I think the more important part is really just the general trend component. Which is by looking at, is their anion basic? If yes, then we can apply this trend where solubility goes up as pH goes down. There's really not much more to it than just that part. And that's, I'm going to kind of leave it at that for that effect. And then we're going to take a look at complex ion formation and its effect. And typically, complex ions, as I kind of mentioned before, are going to form when we have a metal cation that combines with kind of multiple small Lewis bases. Which these are probably the most common ones, like ammonia, cyanide, hydroxide, chloride, just like other halides as well. Those are kind of common Lewis bases. Now, if we have multiple Lewis bases that combine with their metal and still make an overall ionic compound, like in terms of the fact that the whole thing is still charged, we can have a cation or an anion as our overall ion charge, doesn't matter. And the biggest thing that kind of is important here is that this formation of these compounds is really favorable. And in fact, there's sometimes its own equilibrium constant referred to as Kf for these compounds, for these complex ions. And the Kf values are usually very, very big. Like oftentimes, like we're talking like things like 10 to like the 40th or 50th power even potentially. So really, really favorable to make. Well, how does that affect things? Well, when you add a Lewis base to a solution where you're trying to dissociate or dissolve a salt, what's going to happen is that Lewis base is going to try to react and basically bind to the metal cation that's there to make these complex ions. And so in effect, it kind of removes the metal ion from your normal kind of salt dissociation equilibrium. And if you're removing a product from your equilibrium, Le Chatelier says that a reaction should move forward. So the end result then would be moving forward, we're going to get a higher solubility. And that's kind of our general trend. And so that's the thing that really I want people to be able to pick out is that anytime we add a Lewis base of any kind, and these are really the most common ones that you're likely to see for these types of problems, adding the Lewis base removes our metal cation, and the net effect is adding this Lewis base is going to increase our solubility. And in fact, in some cases, it increases it dramatically. You can have things like silver chloride as your starting salt that are not soluble really in water at all. And you can add something like cyanide in just a small concentration, and then you can dissolve almost all of your silver chloride by using kind of this effect. And so it is a very powerful tool for dissolving things that aren't normally very soluble. And that's kind of a kind of real kind of practical application of kind of some of these different solubility trends or things that affect solubility. This is a really good way to get things to dissolve in solution that aren't normally very soluble. All right, the last thing we're going to talk about in this chapter is going to deal with kind of the reverse of this solubility, and that's the idea of precipitation. And so for the idea of precipitation, what we're actually going to look at is the same kind of KSP type equilibria that we've been talking about, but now we're going to go back and use our reaction quotient that we talked about in our previous chapters before as well. And so how this is going to work is if we're given concentrations of different things that are in solution, we can use the reaction quotient to help us figure out, like, will a precipitate form or will a precipitate not form? Or likewise, we can actually kind of set these two equal to each other, because that's when basically precipitation would begin. So any problem that talks about like precipitation beginning, precipitation begins when Q and KSP are equal to each other. And then in general, if you're just trying to figure out, like, we mix these things together, will a precipitate form? As far as like that kind of question, now you're comparing Q and KSP. If Q is smaller than KSP, that means more solid can still dissolve, or in the case if we just combine the ions together, we can combine more of the ions before we really truly get the solid, and so no precipitate would form. But if Q is bigger than KSP, that means in order to get to equilibrium, we have too many ions in solution. So to get to equilibrium, we will be making a solid, or we will be forming a precipitate in that case. Now, one of the other things we can kind of do with this idea of precipitation going backwards, we can kind of compare compounds. Like in this one, we have a solution that contains 2.0 times 10 to the minus 4 molar silver plus, and 1.5 times 10 to the minus 3 molar lead 2 plus. And then we're asked, if sodium iodide is added to the solution, will silver iodide or lead iodide precipitate out first? And at what sodium iodide concentration would that precipitation begin? So a couple things here with this. When we're looking at the precipitation of ions, it's important to note that usually we can compare KSP values to a small extent to figure out which ion should come out first. And for things to precipitate first, we want them to be less soluble. So generally, the smaller KSPs are going to precipitate first, but there's kind of an added piece you want to be very careful of. And that added piece that you really want to be careful of has to do with the fact that the things that precipitate first are actually the things that have the lowest molar solubility, not the smallest KSP, which is a slight difference, but a very important one. Right, so what I'm going to do, I'm going to kind of go back to my whiteboard, and we're going to take a look at how we actually set up and try and solve this problem. And in general, if we're going through this example, what I'm going to do as far as kind of a starting point is I really want to find the molar solubility for the silver iodide and the lead iodide to see which one will actually precipitate first. Right, and so the way I can do that, let's start with the silver iodide, and we'll see why I kind of have to do this as well. For silver iodide, our KSP, our KSP in terms of our molar solubility calculation is really just going to be X times X, because there's only the two ions that are going to form. And so that's going to give me a KSP of about 8.3 times 10 to the minus 17 that we're given. And then I can solve my X value for that, which I'll solve in just a second. I can do the same thing for the lead iodide, right? So here my KSP would be, instead of X times X, it's actually X times the quantity 2X squared. Then has to be equal to its KSP, which was 7.9 times 10 to the minus 9. Now, and I've kind of been showing this in the whiteboard that I haven't displayed here, so I'll kind of come back to here. Sorry for that. So I have my silver iodide. My KSP is X times X. This is because I have the two ions that it's breaking up into. I have my KSP value, and then I can solve for this X. Look at that. It looks like I get about 9.1 times 10 to the minus 9th for my molar solubility. So really, really small solubility. Now, if I do the same for my lead iodide here that I've set up, which is this X times the quantity 2X squared, and just as a general kind of rule of thumb, as you're setting up these equations, if you have two of a particular ion, that means for molar solubility, it is going to be 2 times the molar solubility, 2x. Basically, it's a 2x from the change in your ice table that we'd set up, then being squared. And just, I guess, to show that real quick, like if we had lead 2 plus our 2 iodide ions as our products, remember for starting with 0 of each, we'd have like plus x plus 2x, right, for x and 2x as their equilibrium concentrations. That's where those values are really coming from. It's from the ice table. Now, solving for that x then, in this case, I can solve for my x from that KSP equation. And I get an x value of about 1.2 or 1.3 times 10 to just the minus third in this case. So in this case, it is kind of the KSP values themselves are different enough that we could pretty much tell that the silver iodide has the much smaller molar solubility by just looking at the KSPs. But in general, it's not just like looking at just the KSP only really works if the two compounds you're comparing break into the same number of ions, right? Because if you have like say silver iodide and like calcium carbonate, which would also break into just 2 ions, then you can just immediately compare their KSP and you don't need to look at anything else because the calculation, if it's only breaking into 2 ions, is going to be the same in terms of actually finding the concentration for our molar solubility. If we have compounds like the two that we were looking at in this problem, though, they have different numbers of ions that they're breaking into, so KSP is being solved for a little bit differently. So it's probably best just to solve for the molar solubility in those cases rather than just try to directly compare the KSP, just to be safe, because there can be differences based on how the molar solubility is calculated. That something might have a slightly bigger KSP, but if it breaks into more ions, the molar solubility might actually be bigger. And so that's something to just kind of look out for in those problems. We're going to look at one more in kind of the examples that I'll do as well for that video. That's basically going to show that for those, like if we have two compounds with the same number of ions, then you can just compare the KSP and move on from there. But the end result of this, I have 2 molar solubility values. The one for silver iodide is less. And so since our molar solubility for the silver iodide is less, I'm going to write this down here. Since my molar solubility for the silver iodide is less, it precipitates first. Right? Because your molar solubility is how much it will dissolve, but precipitation is all about going backwards. And so the smaller your molar solubility, the faster that ion will generally precipitate. So in our case, the silver should be the first of these ions to precipitate from our solution in the problem that we were given here. And so now what we have the 2.0 times 10 to the minus 4 silver ions. We know these should precipitate first before the lead. And the next part of this problem is at what sodium iodide concentration would the precipitation begin? And this part actually ends up being fairly easy because basically what we're going to do is just set up our equation, like the reaction for the KSP here for the silver iodide, use the silver plus concentration that we already have, and just figure out what concentration of iodide do we need for the precipitation to begin. And so setting that part up, I can write a reaction, which is that we have silver iodide as a solid going to our silver plus and I minus. And all that's really important here is that we already know the KSP, right? KSP for this reaction was, they told us from up above, that 8.3 times 10 to the minus 17. And then this needs to equal my silver concentration times my iodide concentration. But in the problem, they actually tell us that our silver concentration is 2.0 times 10 to the minus 4. So all I need to do is actually just plug that in for my silver concentration and figure out what iodide concentration is necessary for all of this to be basically be equal to my KSP. That's when precipitation should start, right? When Q and KSP are equal. So which is effectively kind of what I'm doing here. So plugging in my value for silver plus and solving for iodine, my iodine concentration is going to equal 8.3 times 10 to the minus 17 divided by that silver concentration is about 2.0 times 10 to the minus 4, excuse me. And when I divide this, I'm going to get about 4.15 or 4.2 if I round it, times 10 to the minus 13 molar for my iodide concentration. So as soon as for the solution that I have, as soon as my iodine concentration reaches 4.2 times 10 to the minus 13 molar, I'm going to start precipitating silver iodide. So silver iodide, not very soluble, precipitates really, really easily. That's basically kind of the takeaway from this, is that we can precipitate a lot of ions with really not a lot of the anions necessarily being present, and that's okay. But that would be our final answer for what we'd kind of solve for in that particular example. I'm going to kind of cut this video here for kind of the starting of our solubility. And then what I'm going to do is have another follow-up video with kind of some walkthrough demonstrations, again, like I've been doing for our last few sections. And that'll wrap up kind of the end of chapter 17 here, which is, as you've probably noticed, one of our longest chapters in terms of just kind of how many things it's really covering. And then our last two chapters will actually be pretty short once we get into those kind of in the next couple days.